Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh. Sejahtera bagi kita semua. Today I want to presentation my PowerPoint. Title of my PowerPoint is Heat Treatment of Steel. Now I want to introduce myself. My name is Kevin Jessen Lubis. I'm from Metalurgi, Mechanical Engineering, Udayana University. Main reference from Metalurgi for the non-metallurgists, second edition. Edited by Arthur C. Riordan. Heat treatment is defined as controlled heating and cooling of the solid metal or alloy by methods designed to change the microstructure to obtain specific properties. Heat treating takes place below the solid temperature of the alloy, and the purpose of the treatment is to change the microstructure and properties of the solid alloy. The ability to tailor properties by heat treatment has contributed greatly to the usefulness of metals and their alloys in a wide variety of applications, ranging from sheet metal for cars and aircraft to razor blades and hardware steels. First, the iron-carbon system. Steels are iron with a small amount of carbon alloy. Iron by itself has limited structural usefulness because it is soft like most pure metals. Carbon as a small interstitial element also can increase the strength of iron by salt solution hardening. However, solubility of carbon in iron is very limited, which imposes limits on solid solution hardening of iron with carbon. A different mechanism of phase transformation occurs when steel is rapidly cooled or quenched from the austenitic phase back down to room temperature. During rapid quenching, there is not enough time for the carbon atoms to rearrange themselves by diffusion. Carbon plays an important role in heat treatment because it expands the temperature range of the austenite stability. Higher carbon content lowers the temperatures. The deep austenite steel such that iron atoms rearrange themselves to form an FCC lattice structure. Under normal conditions, austenite cannot exist at room temperature in plain carbon steels, but only at elevated temperatures within the austenite area. Austenitizing can be the first part of an annealing treatment or the first step in the concerning hardening of steels. Carbon is almost insoluble in infrared because the interstitial position available in the BCC lattice are not large enough to accommodate it. However, carbon is more soluble in austenite because the larger interstices in the BCC lattice are considerably more accommodating to carbon. When austenite steel is cooled back down to the region of the stable ferrite, the amount of dissolved carbon in the prior grains of the cannot be accommodated by the BCC lattice of the newly formed ferrite. Excess carbon too small excite the ferrite grains during the phase transformation. During relatively slow cooling, the excess carbon atoms move by diffusion and combine with iron to form a new phase called cementite. The cementite phase is iron carbide with the chemical composition of Fi3C. Next, common phase in the steel. 1. Cementite and ferrite formation. The discussion centers on the transformation of austenite in steels with three types or rivals or carbon alloy. Ectotoid steels with carbon content near the ectotoid point of 0.77%. Hypoactectoid steels with carbon content below the actectoid composition. Hyperactectoid steels with carbon content above the actectoid composition. Actectoid steels and chloride formation. The definition of a actectoid point on a phase diagram is the solid solution version of a actectic melting point, like a actectic transformation during solidification. Actectoid points on a phase diagram is where a single solid phase transforms completely at one temperature into a mixture of two or more totally new solid phase. Hypoactectoid steels. Steels with less than 0.77% C are called hypoactectoid steels, when low carbon steels or medium carbon steels are slowly cooled from the actinic phase. Some low carbon ferrite forms first along actinic grain boundaries in the two-phase region of the phase diagram. As the ferrite forms excess carbon diffuse away from effective growth of ferrite during further cooling. This enriches the remaining actinide with more carbon. Hyperactectoid steels have carbon contents greater than an actectoid composition of 0.77 yg%C. As the dissolved carbon increases in the austenite, the iron atoms are pushed further apart. These strains are chemical bonds, and there is a limit how much strain energy the austenite can withstand. Ultimately, kemenatite forms in austenite when carbon exceeds the solubility limit. Excess carbon will be present as separate kemenite grains mixed in the austenite grains. That is, the microstructure will be a two-phase mixture of austenite and kemenite. 2. Martensite. Martensite is a metal-stable structure that forms during rapid cooling of austenite. Unlike the isothermal decomposition of phase constituents by diffusion, martensite is not phase associated with thermal equilibrium. Thus, it does not appear on the iron-carbon equilibrium phase diagram. In contrast, the mechanism of martensitic transformation is a diffusionless process, where rapid change in the temperature causes displacement of atoms and individual atomic moments of less than 1 atomic spacing. The transformation is a sudden and systematic shifting or shearing of the iron atoms into a BCT structure. Because a BCT lattice cannot accommodate all of the carbon dissolved in the prior austenite phase. 3. Bainite. Bainite is a distinct stable phase in steel that occurs when cooling rates are not notched to produce martensite but are still phase nodes, so that carbon does not have enough time to diffuse to form pyrite. Like pyrite, the constituent phase of bainites are ferrite and kementite. However, the shapes of the phase are very different in ferrite and bainite. Ferrite and kementite both have a lamellar morphology as nodes. In contrast, the ferrite in bainite has an ocular morphology and the carbides are discrete particles. Because of this morphological difference, bainite has much different property characteristics than ferrite. In general, bainitic steels have high strength coupled with good sharpness, whereas pyrrolitic steels have a strength with poor toughness. The bainite is the lighter constituent growing out from the prior austenite grain boundaries. A thin white line is superposed along the old austenite grain boundaries on the micrograph. This illustrates the different internal structure of bainite and pyrite. Whereas as cementite is present pyrite as planes distributed between plates or thread. In bainite it is present as filaments and or small particles dispersed in a varied matrix. Next, critical temperatures and transformation diagrams. Three important critical temperatures in steel heat treatment are A1, critical temperature for the start of the transformation to austenite, and so-called eutectoid temperature, which is the minimum temperature required for the austenite to form. A1 is also referred to as the lower critical temperature. A3 critical temperature for complete transformation of the A+2 phase mixture into 100% austenite or G, referred to as upper critical temperature. A3 is the high temperature boundary of the A+ solid solution phase region with carbon contents below the eutectoid composition of 0.77% C. ACM, critical temperature for the complete transformation of the Z plus Fi3 phase mixed into 100% austenite. The ACM critical temperature is the high temperature boundary of the cementite in the solid solution with austenite in the hypereutectoid steels. Next, transformation diagrams. The kinetic aspect of phase transformation are in person as equilibrium diagrams for the heat treatment of steels. Any particle heat treatment requires heating and or cooling. Therefore, another important tool in steel heat treatment is the use of transformation diagrams that plot phase transformation as a function of temperature and either time or the rate temperature change. In general, there are 4 different types of transformation diagrams that can be distinguished. They include 1. Isothermal transformation diagrams describing of austenite tearing hasting or sometimes as ITH diagrams. Isothermal transformation or IT diagrams, also referred to as time temperature transformation or TTT diagrams, describing the composition of austenite. 3. Continuous heating transformation diagrams. 4. Continuous cooling transformation diagrams. Annealing and normalizing. General annealing thermal cycles. Annealing cycles are varied according to the temperature and the method of use. Annealing temperatures may be classified as subcritical annealing below the lower critical temperature A1. 2. Intercritical annealing above A1 but below the upper critical temperature. A3 in hypoeutectoid steel or ACM in hypereutectoid steels. 3. Supercritical annealing to achieve full austenitization of either hypo or hypereutectoid steel. Annealing guidelines. The metallurgy principles of annealing cycles can be described by the following 7 rules, which may be used as guidelines for the development of success and efficient annealing schedules. Rule 1. The more homogeneous the structure of the S-authenticized steel, the more completely similar will be the structure of the annealed steel. Conversely, the more heterogeneous the structure of the S-authenticized steel, the more narrowly spheroidal will be the annealed carbide structure. Rule 2. The softer condition in the steel is usually developed by austenitizing at a temperature less than 55 derajat Celsius or 100 derajat Fahrenheit above A1 and transforming at a temperature less than 55 derajat Celsius or 100 derajat Fahrenheit below A1. Rule 3. Because very long times may be required for complete transformation at temperatures less than 55 derajat Celsius below A1, allow most of the transformation to take place at the higher temperature, where a soft product is formed, and finish the transformation at a lower temperature, where the time required for completion of transformation is short. Rule 4. After the steel has been austenitized, cool the transformation temperatures as rapidly as feasible in order to minimize the total duration of the annealing operation. Rule 5. After the steel has been completely transformed at the temperature that produces the desired microstructure and hardness, cool to room temperature as rapidly as feasible to discourage further the total time of annealing. Rule 6. To ensure a minimum of lamellar preload, relate the structure annealed to 0.70 to 0.90% C-tool steels and other allowably medium carbon steels. Preheat for several hours at the temperatures approximately 28 derajat Celsius, below the lower critical temperature or A1, before switching and transforming as usual. Rule 7. To obtain minimum hardness is annealed hypertectoid alloys tool steels. Heat the austenitizing temperature for a long time, then transform as usual. Types of annealing treatment. Annealing treatment have various metallurgical purposes such as stress recrystallization and spheroidization. 1. Stress relief annealing. Annealing at a subcritical temperatures includes 3 different temperature regions. The first is temperature range for stress relief annealing. Annealing involves uniform heating of a structure or portion thereof and holding at this temperature for a predetermined period of time, followed by uniform cooling. 2. Recrystallization annealing. When cold work metals and heat the sufficiently high temperature, the badly deformed cooled work grains are replaced by new strain-free grains. This process is referred to as recrystallization, which is distinct from the recovery process starting stress relief at a constant temperature. recovery starts rapidly and then decreases with time. 3. Sparrowaging. Depending on the time temperature exposure of a steel, the cementite carbides in a steel can form different morphologies such as the lamellar cementite of pyrite or a network of cementite along pure austenite grain boundaries in hypersectoid steel. The shape and distribution of the carbides can be modified by heat treatment, and spheroidization treatments are used to produce carbides with a more spherical morphology. Nobilizing of steel. Steel is nobilized to refine grain size, make its structure more uniform, make it more responsive to hardening, and to improve machinability. When steel is heated to a high temperature, carbon can readily diffuse, resulting in a reasonably uniform composition from one area to the next. The steel is then more homogeneous and will respond to the heat treatment more uniformly. Furnace heating and induction heating. Furnace heating. Treating furnace can be generally classified as either batch or continuous furnace. Batch type furnace, where loads are placed in the furnace and its loads are brought up to temperature together, and depending on the process, the furnace may or may not be cooled before it is opened and the load removed. Continuous type furnace, which operates in uninterrupted cycles and workpiece pass over stationary hearth or the hearth itself. Induction heating is a method of heating electrically conductive materials by the application of a waving magnetic field whose lines of force enter the workpiece. In this process, the varying magnetic field induces an electric potential or voltage, which can then create an electric current depending on the state and the electrical characteristics of the workpiece. These so-called eddy currents dissipate energy and produce heat by pulling against the resistance of the important conductor. Other advantages of induction heat treating which stem from this non-contact method and its generation of heat within the workpiece are: 1. Ease of automation and control, 2. Reduce floor space requirements, 3. Quiet and clean working conditions, 4. Suitability for the integration in a production line, a general work area, 2. The elimination of secondary or repetitive heating. Last, self-monitoring capability. Hardening and tempering. Hardening of steel involves a three-step process of austenitization, quenching, and tempering. Quenching refers to the process of rapidly killing metal parts from the austenitizing or solution treating temperature, typically from within the range of 815 to 870 derajat for hardening medium and low carbon steel temperatures as high as 1232 derajat C for hardening specific grades of high-speed steels. Quench media successful Hardening usually means achieving the required microstructure, kernel strands of toughness, while minimizing residual stress, distortion, and the possibility of cracking. The selection of consent depends on the hardenability of the particular alloy, the section thickness, and the solve involved, and the cooling rates needed to achieve the desired microstructure. The most common consent media are either liquids or gases. The liquid consents commonly used include air that may contain operative additives, water, aqueous polymer solution, water that may contain salts or caustic additives. Tempering. Hardness steel can be tempered to reduce hardness to increase toughness. All tempering operations are carried out at temperatures below the lower critical temperatures or A1 of alternate formation. When carbon or low alloy orthostatic steels can be tempered in lower or higher temperatures range, depending on the balance of properties required. An example of a microstructure containing tempered magnetite in the microbe, the carbides or cementite appear as small black etching particles. Then it is difficult for the metallographer to distinguish between tempered metalsite and bainite. A microbe of a steel with tempered martensite and some bainite. Cold treating of steel. Cold treating may also be used to improve wear resistance in materials such as tool steels, high carbon martensite stainless steels, and carbureted alloy steels form applications in which the presence of return of cyanide may result in excessive wear. Transformation in sample may cause cracking and or dimensional change that can promote failure. In some distance, more than 50% retained austenite has been observed. In such case, no delay in tempering after cold and is permitted, or cracking can develop readily. Process limitation. In some applications which explicit amounts of retained austenite are considered beneficial, cold treating might be detrimental. Moreover, multiple tempering rather than alternative phase sample cycling is generally more practical for transforming retained austenite in high span and high carbon, high chromium steels. Arnold testing lower than expert higher readings may indicate excessive retained austenite. Significant increase in the readings as a result of the treatment indicate conversion of austenite to martensite. Superficial hardness readings such as R15N can show even more significant change. Precipitation hardening steels. Specification of the precipitation hardening steels may include a mandatory deep freeze after solution treatment and prior to a shrink fit. Cooling the inner member of a complex part to below ambient temperature can be a useful way of providing an interference fit. Case hardening. Case hardening is a generic term used for several processes. The good hard will resistant surface lower on a part. This combination of hard surface and resistance to break edge on impact is useful in parts such as can or rain gear that must have a very hard surface to resist wear, along with a choke interior to resist the impact that occurs during operation. There are two distinctly different approaches to the various methods for surface hardening. One, Foley and casting methods that involve an intentional build-up or addition of a new layer. Two, surface treatments that involve surface and subsurface modification without any international build-up or increase in part dimensions. Case hardening by surface treatment can be classified further as diffusion treatments or localized heating treatments. Diffusion methods introduce allowing elements that enter the surface by diffusion, either as solid solution agents or as hardenability agents that assist martensite formation during subsequent quenching. Diffusion methods include carbon nitriding, nitrobridging, titanium carbon diffusion, Toyota diffusion process. Localized heating methods for case hardening include flame hardening, induction hardening, laser hardening, electron beam hardening, ion implantation, use of arc lamps. Diffusion methods of case hardening. Carburizing is the addition of the carbon to the surface of low carbon steels at the temperatures at which austenite with its high solubility for carbon is the stable crystal structure. Hardening is accomplished when the high carbon surface layer is quenched to form martensite, so the high carbon martensite case with good and fatigue resistance is suppressed on top low carbon steel core. Of the various diffusion methods, gas carburization is the most widely used, followed by nitriding and carbon nitriding. A number of different types of the conventional heat treating furnace are used for gas carburizing, including pit rotary box and continuous types. Nitriding is a surface hardening heat treatment that introduces nitrogen into the surface of steel while it is the ferrite condition. Nitriding is similar carburizing in that surface composition is altered, but different in the nitrogen is added into ferrite instead of austenite. Nitriding can be accomplished with a minimum of distillation and with excellent dimensional control. Other diffusion methods. Surface hardening with carbon and nitrogen offers precision temperatures between those of carburizing and nitriding. In general, there are three techniques that use carbon and nitrogen for surface hardening: carbon nitriding, austenitic nitrocarburizing, ferrite nitrocarburizing. Next, localized hardening process. Flame hardening consists of hardening in the surface of steel by heating with an oxyethylene or oxyhydrogen tert, and the immediately condensing with water. The result is hard surface have a layer of molten side over a softer interior core with a varied structure. There is no change in composition, and for the flame hardened steel must have adequate carbon content for the desired surface hardness. Induction heating is extremely versatile heating method that can perform uniform surface hardening, local surface hardening, through hardening, and tempering of hardened piece. Heating is accomplished by placing a steel part in the magnetic field generated by high-frequency alternating current, or AC, passing through an inductor, usually a water-covered coil. Laser surface heat treatment is widely used to harden localized areas of steel and coarse-hardened machine components. The heat generated by the absorption of the laser light is controlled to prevent melting and is therefore used in the selective austenization of local surface regions, which transform to molten side as a result of rapid cooling by the conduction of heat into the bulk of the workpiece. Electron beam or IB hardening. Like laser treatment is used to harden the surface of steel. The IB heat treating process uses a concentrated beam of high-frequency electron as an energy source to heat select surface areas of various parts. Like laser beam hardening, the IB process eliminates the need for quenchance but requires a sufficient workpiece mass to permit self-quenching. Self-hardening. The part is immersed in high conductivity heating medium such as molten lead or salt bath. Immersion time is only long enough to completely heat the outer surface. Quenching follows. The core is never heated to a temperature high enough to support the formation of austenite. The cell is metastatic while the core is essentially pyrolytic. Cold workdays are a typical application. Next. Heat treating equipment. Generally, furnaces are classified by heat source or combustion of fuel, or by conversion of electric energy to heat, and by two broad categories: batch and continuous full-fired combustion furnaces are most widely used, but electrically heat furnaces are used when they offer advantages that cannot always be measured in terms of fuel cost. Batch furnaces are loaded with charge and cost per operation established heating cycle. After the cycle is complete, parts may be cooled in the furnace after the heat is turned off, or a method such as quenching in water or oil may be used. Types of batch furnace include 1. Box furnace, 2. Car bottom furnace, 3. Pit furnace, 4. Bell and hood furnace, 5. Elevating hard furnace, 6. Integral quench furnace, and last, deep up furnace. Continuous furnaces are basically of the in one and of the other type and are ordinarily used the continuous full production. They can accommodate a variety of heat treatments. Examples are 1. Roller heart furnace, 2. Moving heart furnace, 3. Washer furnace, 4. Shaker heart furnace, and last rotary return furnace. Furnace atmosphere. In many heat treating operations, parts must be heated under conditions that prevent scaling and or loss of carbon. As steel is heated, its surface becomes more active chemically. Vacuum furnace. Heat chambers in this type of furnace are evacuated to a very low level depending on the material and process by which metal is being treated. In most operations, evacuation is to approximately 1/3 the unit for the measurement of vacuum. Plasma furnace. A glow-discharge plasma occurs when a direct current or DC of a few hundred volts is applied to two metal electrodes in an enclosure evacuate a few hundred pascals of pressure. The resulting plasma is essentially a low-pressure ionogen gas, and the process can be used to introduce carbon-bearing ions to the surface of steel for subsequent diffusion below the surface. Fluidized bed furnace consists of a bed of mobile inert particles, usually aluminum oxide, suspended by the combustion of a fuel-air mixture pouring upward through the bed. Components being treated are immersed in the fluidized bed, which acts like a liquid and are heated by it. Heat transfer rates are up to 10 times higher than those available in a conventional open-fired furnace. And the last, salt and liquid bed hot furnace. Bed of molten salt or metal can be used for both heat treating and heating applications. Both furnaces are unique in the media being melt is the source of heat for this operation. Heating in a molten metal usually is an age-old practice. Pot-type furnace containing molten and lead provides an effective means of heating steel parts. So much from me. Thank you.